Sir,
Yes. Shall we start?
after the completion of the session, please provide a
Yeah.
link for that link.
So it will be available. Okay, I will. Uh, I will have to upload that on YouTube, so it will take some time. But by tomorrow morning, I will surely upload. I will try to upload it after the lecture only. But if it
Okay, sir. Okay, thank
takes time to upload, then in the morning you will get the link on the same Google Sheet.
you. Okay,
And slide also will be available in the same folder. I will post the slides
okay,
also.
okay, sir. Thank you.
Okay, so let us start. Let us begin today's session. Okay, I'm Gagan Meena and I'm doing PhD from Electrical Engineering Department at IIT Bombay. So this will be the agenda for the live session. So we will first see the overview of week 2, a very brief overview. Then we will discuss some questions regarding that week 2. And then also in between with questions, I will also discuss some important topics mentioned in the question. And then we will take your doubts regarding the week 2 material. Before starting the uh, overview of week 2, I would like to remind you that deadline for assignment 3 and 4 is 15th and 22nd Feb respectively. So please try to submit the assignment before deadline. And you can find the live sessions recording on this link. Before going to the overview of week 2, we will first discuss two topics from the week 1. One is regarding the doubt which was raised by someone regarding the Energy Service Interface (ESI). So ESI is an interface between. It is mainly for the customer domain or the consumer domain, and it is a gateway. So it is a gateway which helps the customer domain to interact or communicate with the other domains like distribution, operation, service provider, and via the advanced metering infrastructure or the internet. And for the communication within the customer domain, it happens through the home area network or LAN. So this ESI is basically a software. It is also called gateway. So it is for interacting with other domains and within the domain itself. Okay, so is there any doubt for ESI? Okay, then let us move to this next topic. There was one more doubt raised for the IEEE 1547 standard. Okay, I will provide the mail ID at the end. I will write in the chat box. So, IEEE 1547 is the standard for interconnection of distributed energy resources to the grid. So it provides several guidelines which the DER has to follow to interconnect itself to the grid. But there were some challenges, some recent occurrences. For example, this Odisha disturbance in May 21, then San Fernando disturbance in 2020, and then Blue Cut wildfire in 2016. So all these disturbances led to a generation loss of more than 1 gigawatt. You can see 1.34 gigawatt in 21. This is a recent one. And all this happened because of misapplication of IEEE 1547. There was no such standard available for interconnection of DERs at the transmission and subtransmission level. So IEEE 1547 mainly concerned with the DERs, which are mainly at distribution level or for microgrids. So because of any lack of uniform interconnection requirements for bulk system connected IBR plants, there were ambiguities and which resulted in inconsistent implementation, and therefore which led to a lack of capability needed to ensure the power system reliability. Because of loss of such a large generation, there are problems in system operation. So if there is an instantaneous loss of such a huge generation, then there will be challenges in operation. So this was the motivation to come up with a new standard. So as a result of this, recently in 2022, IEEE 2800 standard has been released for transmission and subtransmission level. So it is a standard for interconnection of interoperability of inverter-based resources interconnecting with associated transmission electric power system. So this is an update to the IEEE 1547. Now India, so we have also come up with the new grid codes in India also based upon this IEEE 2800 standards. Now all the solar and wind new plants of solar and wind, they have to follow those guidelines. Let us see what are those guidelines in very briefly. It is just a flowchart, and you can go through these. If you want to go through them in details, then I have provided the links. You can go and visit, and entire document is there. You can read in great detail. All the standards have been mentioned. All the requirements have been mentioned. So these are so this slide shows the IEEE standard technical minimum capability requirements. So there are general requirements which are like measurement accuracy, control prioritization, control responses. But the other are, and there are also some guidelines for test and verification requirement for each of the new plants which are to be established or connected to the grid. And there, while operation, there are requirements for frequency response, for reactive power, voltage control, and for power quality, ride through capability, performance, protection. So we will not go through the details of these because it will take time and each topic itself will take time. So I've just mentioned this so that you can, in future, you come across IEEE 2800, you know that there is some standard, and if you want to refer to it, you can go through it. So have you heard of this low voltage ride through capability or high voltage ride through capability? Anyone? Okay, so actually, so these are the requirements which have been now mentioned. Like for low voltage ride through means that the solar or wind farm which is connected to the grid, it has to carry out, continue to be connected to the grid even when the voltage is low. So there is a limit to that voltage that is mentioned in the standards, that up to a certain voltage they have to be connected for certain duration of time. If the voltage goes below that, then also they have to continue for some time But if it goes below a threshold, then they can disconnect or they can stop feeding into the grid. So such time of operations requirement is there, and which is made possible through these LVRT control, which are embedded into the control of solar and wind inverters. So now the new IBRs, they will have to incorporate these controls within their inverters so that they can meet the new standards, so that we can have continuity of supply. Suppose there is a actually we talk about in the previous slide we saw three incidences. Which were the incidences which happened somewhere else? The disturbance was far away from the place where the converter IBR was connected to the grid, but still IBR was was disconnected because there were no such guidelines. So there was an instantaneous disconnection of IBR from the system, which led to generation loss. But now they have guidelines that if there is some disturbance and voltage goes beyond a threshold, then only you can cut your supply. Otherwise, you have to remain connected. But before there was no such guidelines, so these incidences happened. In India, also such incidences have occurred. So, but now these new guidelines will help us manage these resources more effectively and ensure reliability of power supply. So let us move to the a very brief overview of week two. So in week two, first of all, we discussed this. This was a continuation of the week one, the elements and technologies of smart grid system, where we discussed this SCADA system and the smart metering. Then we discussed about two distributed energy resources, solar and wind. So in SCADA, SCADA majorly it consists of, so SCADA, full form of SCADA. Who can tell the full form of SCADA?
Supervisory control and data acquisition.
Correct. So supervisory control and data acquisition, and it has three major components: the master station, remote control, remote terminal units or remote tele control units, then communication system. And then master station also has these different components: acquisition server, then real-time database server, historical servers are there to keep track of historical data. Then application servers are there which run some applications. And then there is operator workstation, which operator can work, they can train, it can be used for training purposes. Then RTU has also these components like data collection application, processing and translation applications. And all these requires communication because SCADA will measure something through IEDs or the sensors, which will communicate the data to the RTUs. RTUs then will communicate the data to the master station. So all this will require communication, which can be wired or wireless. Then we talked about the smart metering, and this is the base. These are the function. This is the functional block diagram of smart meter. So first the signal is acquired. Then we do signal conditioning, where we have different types of filters. Because we don't want harmonics. We only want the fundamental frequency. So we need filter. We also have this anti-aliasing filter also. So that's sometimes some higher frequency components they behave like fundamental frequency components. So we have to remove them also. Then after the signal is conditioned, the output goes to the ADC. Then everything the computation happens in digital domain. Then it is communicated to the data management system or the energy control center of the utility. Then what is the significance of aliasing filter? Aliasing filter is same. I told that There are some high frequency components which behave like fundamental frequency component, but we only want the fundamental frequency component because we want to measure current and voltage. So we want to measure them. Harmonics we don't need. And to avoid those components which behave like fundamental but actually are higher frequency components, we use that filter so that we can get the pure sinusoid. Is it a kind of low pass filter or high pass filter? No, it will be low pass filter only because it higher we don't want the higher frequency component, right? So we want the fundamental. So it will only pass the fundamental component. And we can also ensure this based upon the Nyquist criteria. We will study about this filter as well as the Nyquist criteria when we will study the digital protection, maybe in the fourth week four, where we will study this phasor estimation. There we will again come to this point, how this is ensured. Is it okay? Okay. Okay, so let us move to the next part. So then we discuss the distributed generation resources. First one, solar. So in solar PV system, there are two types: grid connected and off grid. So can anyone tell which one of these two system is shown in this figure? Is this grid connected or off grid PV system? Which one? Correct, grid connected. Because we can see here the this shows the bidirectional flow between the system PV system and the electric utility. So the PV system is there, energy conversion happens here. Then this is a converter which will convert DC because here we have DC. Here it is DC and here is the AC. So this DC to AC conversion is done through converters. And even for storing into the battery also we need some control. So because there is also sometimes a DC converter inside this because the output voltage of solar panel is less, so we want to boost it to a required voltage. For that we need either we use boost or buck boost converters. Then now it is DC here. So this is DC because it will go to battery storage. It will store. What are the buck boost converter? So have you heard of boost converter, buck converter? Boost, I know. Yeah. So boost is for uh, boosting the voltage. We say step. We can say similar to step up transformer in DC domain. So it will step up the voltage. Similarly, the buck will step down the voltage. But the buck boost can do both the conversion based upon the control of duty cycle. So how we control the duty cycle that will determine which operation the converter is doing, buck or boost.
Sir,
Okay.
I was thinking also.
See, sorry. Yes. Do you want to say something?
Yeah.
Yes.
Everybody
Yes.
is saying that I have small doubts, sir.
Yes. Yes.
Uh, Everybody is saying that the output of the PV system is connected to grid.
Mm-hmm.
Okay, what do you mean by grid, sir? How this output of the PV system is connected to grid? Because the output of the PV system, I don't know how much voltage we get from that PV system. how you are connecting the output of this PV system to a grid. Generally, I don't know about this, but I would like to know, sir.
So good question and a practical one. So it's a question related to practical implementation. So we can, if we see this diagram only, so if we consider this, in actual farm there are several units. So several units will be there. Suppose there is it's a 10 megawatt plant, solar plant. Then it will be divided into say 1 megawatt. So there will be 10 units of 1 megawatt each. So if we consider these are those 10 units, each one of them are feeding 1 megawatt. So the- they will be giving DC output. So we'll be having one converter here, DC to AC converter for each unit.
Sir, at what voltage level, sir?
This is low voltage level. Around this DC is around between 400 to 600 we can say. Depends upon the inverter and the converter. So this it can be 400 to 600 volts. Then this it will be converted into AC. Then there will be one transformer here. Each of these units will be having transformer, which will boost the voltage to a higher level. Okay, then this again this will go to one block. There will be one. So you can this is 33 or it can be 11 kV also. Then this will be the transformer which will again boost the voltage depending upon at what level you are connecting this plant. If you are connecting it to 220, 110, 66 kV, accordingly you have to boost the voltage. So we have several strings. So one unit be divided into several units, sub units, and each one will be having their own inverter and a transformer. And entire energy will be then again pooled to one concentration. We can say the main substation of that farm. There again one transformer will be there which will boost the voltage which will be adequate enough to connect it to the grid at that desired adequate voltage level. Now it depends upon the size of the plant and at what voltage level you want to connect. Is it clear?
Yes, sir. Thank you.
Maybe next time, if I get some practical layout of a farm, I will share. I will show in the class.
Sir, I have a one question. In
Yes,
grid connected mode, we use a reference. The grid signal is itself a reference signal.
correct.
So, if there is no electricity, then the PV panel can't generate the electricity.
Hmm.
Uh,
Yes.
just could you please provide some light on this?
See, there are is two type of converters. One is this grid farming converters and grid feeding converters. The converters that or IBRs that we have right now, as per the standards that we have this grid feeding converters, and they take so they will feed the required P and Q. So their control system will be designed such that their set point will be P and Q, the desired active power and reactive power. So control system will try to achieve that. So they will not care about voltage and frequency. So to provide this P and Q, desired P and Q, they will take this V and F reference from the grid. Suppose this is, you can say, a solar farm, and then here is this is grid, and this is our solar PV. This is the point of common coupling where we are connecting the farm to the grid. So here the voltage and frequency is the same which this grid is providing. So the control of the grid feeding converters are such that they will take this voltage and frequency response and frequency and voltage reference, and from that we have this PLL. So this PLL is required to synchronize this output of PV to the grid. So this also provides the reference theta, the angle. So inside there is uh, to make the control simple, we use PI controllers, and we want to track voltage and currents which are AC sinusoids. And if we use PI controller with sinusoids, then the control design become a little difficult, cumbersome, complex. There are PR controllers which can do that, but we most of the controller, the IBRs inverters that we have, we generally use PI controllers because they are very simple. So, but they cannot operate with sinusoids. They will give large errors if we use the sinusoids. So for that, we have to convert these sinusoid quantities V and current and voltage into constant DC. For that, we use some these. Suppose these three ABC, VA, VB, VC are the three phase voltages. So we need constant quantities. So we will get some VD, VQ. So this is ABC to DQ transform. We will study this in future lectures also. Now these are constant, so we can use the PI or conventional PI controllers. But this also need one reference, this theta information, which is given by this PL. So the conventional, all the inverters that we have right now, they need voltage and frequency reference to feed P and Q into the grid. But if they don't have that reference, as per the regulation, they have to stop. So they cannot operate in islanded mode.
That means for islanding mode, we have that grid farming converters, is it?
Yes. Uh, so there are standalone system, right? This off-grid system. Whatever they are generating, they can directly feed it to the battery. That can be done. One thing is that, but they will not be able to maintain. They may not be able to maintain V and F. They are not designed for maintaining V and F. But if you suppose you are saying, if the there is a microgrid and it has several loads, and this is the one generator, suppose solar, and there are loads which require a fixed voltage and frequency. So since grid is not there, it does not the solar does not have V and F reference. So it may not be able to. It will be able to generate P and Q, but it will not be able to uh, regulate the voltage and frequency. So for loads, that will be a problem. Because if the microgrid is islanded, we need some generator which we can say it is a slack bus, which can provide that constant voltage and frequency. But their control is not designed in that way, so they cannot provide that constant frequency and voltage. They will just keep on pushing power P and Q. They will not care if the voltage is rising or because right now what happens in distribution system, this is one of the problems that because we have these grid feeding converters, so in daytime when the generation is more, So they are feeding P and Q. They are feeding the active power. And because of that, the voltage is rising above 240 volts. Because they are not designed to regulate the voltage, to maintain a constant voltage. So that is a problem. And if in microgrid we have such generator which does not provide a constant V and F, the loads will not be able to operate at such a high voltage. They have a limited operational region, so within plus minus 5, 6, or 10% voltage. But beyond that, how loads will not work. They will be damaged. So the alternative of them is this grid farming converters. So they can provide this voltage and frequency reference. So the research is now going into this direction. Some of the converters may now have this P and F reference if they are grid farming. Is it okay? Is it okay, Akansh?
Yes, sir. One more question. If
Hmm.
there is absence of reference signal at that time, can a PV charge the battery?
Yes, it can charge the battery if it is because some inverters are designed such that if the reference is not there, they are designed to shut down. But if that control is not there and the storage is there, they can charge. It depends upon how the control is designed. If they are designed that without the grid V and F reference, they can charge the battery, they can charge. Otherwise, they will be just the they will be curtailing the renewable energy will be just wasted. It will not be used. So it all depends upon the embedded control which is inside the inverter. Okay, so but grid farming can do that. I think we will again will come across this term in the future lectures also, and more about this transformation, DQ transformation will also come again. Okay, so let us move further. So then this is the standalone PV system. So here we have this PV array. Then we have a charge controller. It will charge the battery. Then this charge controller output will go to the DC load. If there are DC load which can directly run on the DC supply. So we have these our all electronic devices like these. They they are DC loads. So they can because we use these adapters. They convert the AC into DC for them. So if we can directly have those, we don't need those adapters. Then if there are some AC loads, then the output of the battery has to go to the inverter, which will then convert this DC output into AC for the AC loads. So can you tell what is the function of this charge controller? Why do we use the charge controller? Okay, so charge controller prevents the battery overcharge and discharge both. Also prevents this. It blocks this reverse current flow, and also it can display the battery status, its health, state of charge, state of health. We will see this again in this week 3. Here we will discuss about different type of storages and the energy management system, the battery management system. different batteries. Then we saw the solar cell modeling and the PV and IV characteristics of the solar, then series parallel connection. Then we saw impact of temperature and solar irradiance on the PV characteristics. So these are the equation. We will see them later. So this is the distribution of all India RES capacity till November 2022. So we have this solar ground mounted and rooftop. So mostly we have this ground mounted because these are big solar farms. Then we have wind power, small hydropower, biomass, and waste to energy. Next, we discuss this wind resource. So we talked about wind turbines. There are two types of wind turbines, right? The horizontal axis and vertical axis turbines. So we generally use horizontal axis turbine because they can provide higher power. Then we saw how the energy conversion happens in the wind energy systems. And there are different types of wind turbine generators, type 1, type 2, 3 and 4. Then we saw the wind power calculation. We saw that P is V square into Cp. So this came from this BETS. So BETS limit gives the maximum Cp, which is 0.593. Then we also talked about the wind power curve and the torque speed characteristics. We will see these things again when we will discuss the questions. So this is the block diagram for the wind energy conversion process. So we have the input wind power which rotates the blades of the turbine. Then there is a gearbox. So why do we need gearbox? Anyone?
This to adjust the speed up.
So to to increase the speed, we can say it will not adjust, but it will increase the speed because the speed of rotor is very less. But the generator, if we need 50 hertz, then we need high RPM. So the gearbox will increase that speed, which is adequate for the
Sir,
generator. Yes.
when the winds are high at that time, the rotor blades will rotate to high speed, na, sir.
When the wind is high, then rotor.
Yeah, when the wind is high, the rotor automatically speed ups. At that time, the gearbox has to adjust the gears to control the speed, right?
In that sense, we can say
To
yes.
maintain the constant speed, sir. To maintain the constant speed.
There are uh, other things also which help in controlling that because the pitch control and yaw control is there. So mainly the pitch control. We want to extract the maximum power from wind. So to get the maximum torque, so we need that pitch control. So blade are pitched. We will see that again in the later slides. The generator is there. Then we have this converter, then the transformer and the power. Then the output is fed to the grid. Now let us move to questions for week 2. So first question is this: which of the following is not a part of remote technical? Oh, sorry, remote terminal unit or remote telecontrol unit. So what is the answer? We already discussed this in the previous slides, and also you have gone through lectures. So who would like to answer? Anyone?
Sir, maybe historical server, I think.
Correct. Historical server is correct. Historical server is part of master station. So all these first three are the components of RTU. So now the next question is, in smart meters, which type of communication technique is used? Telephone network, Ethernet, Zigbee, T. Correct. So we can have all these communication techniques. So which one of them is wired and which one is wireless? Can you tell?
Zigbee is wireless.
Correct. Another two are wired.
Wired.
So now next question is, third generation of solar cells are made of? So we have this was there in the lecture. Any guesses? Thin film, advanced thin film, or silicon wafer based? D. No, D is not correct. Answer is B. Advanced thin film solar technology. So answer, the first generation is the silicon wafer based solar cell. Then we had this multi-layer thin film solar cell. Then the third generation is this advanced thin film solar technology. Now we will see some new technologies from solar perspective. So here we can see, I think you would have heard of these floating solar plants. Yes. So right now the largest solar floating farm is this in China, this 320 megawatt. Recently, India also has come up with this NTPC Ramagundam 100 megawatt. This has been commissioned recently in 2022. So where in MP? I don't know about the one in MP. I think its capacity is less. I have mentioned those which have high capacity. Do you know what is the capacity of that plant? Okay, no problem. We can check. So I have listed only those which are the highest capacity. So this one is the highest installed capacity of floating solar plant in India, followed by this one in Kerala, 92 megawatt. There are others also smaller than these. So in this first figure is the same for this 100 megawatt and this solar floating plant in Telangana. And this figure is of one this floating solar plant in Switzerland in Alps. So they have installed this in a very this is a very high altitude lake, around 1.8 kilometers above the mean sea level. You can also see the snow here. So it is one of the lakes in Alps. So there are some benefits of installing these solar plants in high altitude. And in general, why do we go for this solar floating plant? What is the benefit of installing this? Means why are we using using this floating solar plant? What advantage do they have over the land-based solar plants? Can you tell? You can make a guess also. to utilize water body. How utilization in what sense? Because if suppose there were some ferries, if some boats also, we can use lake or river open space. Yes, in that sense, yeah. Because if a lake is there and it is first, so I can correct this point that we can rephrase it like, so we don't need any land. Land cost is saved. We can use a reservoir which is not used for any transportation purpose or anything, and we can save cost in that sense. Another one of the biggest advantage is maybe evaporation. That is also true. Evaporation of water is also reduced, but lake is very large, very big, and this solar farm will occupy only a fraction, at one, even less than, maybe less than 1%. This this Alps, this solar plant occupies even less than 1% of the lake.
So, by constructing these PV cells on lakes,
Hmm.
to effectively utilize the solar, what do you say, solar rays, sir.
Solar rays. We cannot
That,
solar rays. We are talking.
sir.
Actually, it depends. If it is
No,
flat, means yes. What do you want to say? Means, can you again say?
uh, that means the insulation will be high, sir.
Installation will be
Not installation, insulation.
insulation. Okay. Yeah, that point is true for these bodies in Alps. I will elaborate on this also. That one of the major advantage of putting solar plant over these land based is cooling effect which these water resources provide. So they will provide natural cooling which will enhance the efficiency of solar panel. Because as the temperature increases, the efficiency of solar reduces. Even the maximum power output will reduce. It is dependent upon the temperature. We will see the PV characteristics. So if we have we install them on water bodies, then first we get the cooling effect. Then if we are installing them at high altitudes, further their temperature is less. Another effect is because of this snow, there is one effect called albedo effect. So snow also again reflects the solar radiation. So irradiance increases, and therefore the output of solar also increases. So that is why they are also going for these high altitude floating solar plants. So this one is the first one, but we have several these solar floating plants in lakes. In Japan has in the sea also, but they have to they need they their installation cost may be high because they have to be prone to these waves, high tides. But in lakes, that challenge is not, that problem is not there. So lakes are better option if we have them. This Three Gorges. This station is also installed on a dam, so it is almost a still water, still waters. Similarly, this in Thailand also they have put it in a dam. So there are some other advancement in solar technologies, like we have these transparent solar panels, solar highways, and solar paint. So have you heard of any of these? Solar panels, transparent solar highways, or solar paints. Have you come across these terms? So transparent solar panels, you can see. normal solar panels, but they are transparent. So we can use them instead of our windows. In Windows, we have these normal glasses. Instead of them, we can use these transparent solar panels. So they will behave as window as well as they will provide us electricity. Right now, they are not economical. So if once the mass production begins, they may become economical. Then they will be used in windows, in big buildings. We have so many now in big, all these tall storied big buildings. We use these glasses, so that can be used. Then we have these solar highways. Recently in China and also in France, they have built these solar highways. So what they do is they on highways on the extreme side, extreme lane, they will have these solar highways. So these are solar panels embedded in the on the road highways. So they can be used to charge the lights to for lighting purpose, and they can also be used for dynamic charging the vehicle electric vehicles. China has also done one pilot project on this, that the electric vehicles they can move slowly over this highway and they can get charged dynamically, wireless charging. That is also possible. Then the third option is this solar paint. So this is a paint, a liquid paint. Once applied on the surface, after drying, it will act as a solar panel and it can produce electricity. So this can be used on vehicles. Or we can paint the buildings, roof. But wireless charging is not economical as losses is huge. Yes, so research is going in that direction, how to reduce the losses, how to increase the efficiency of dynamic charging. But still, losses are dynamic charging requires a very small gap between the those what we call two plates that we use for charging. If the gap between them is very small, then right now efficiency is good. But how to reduce that gap and how to increase efficiency when the gap is more, that is still a ongoing research topic. So many things are going on, but still we can use them. In future we may see these things. So this is the next question. So define the characteristic curve in the y-axis variable, x-axis variable form. So first curve is this. This is the second curve. So which curve is this? Can you tell? What are the axes? V, I, P, V, I, V. What is the? Which one is the right option? Anyway, A, I, V, and P. V. Correct. So this is current axis, and this is voltage, and this is PV, power, P and V, power and voltage. So which effect is being shown here? So here we can see if we go from in this direction, current is short circuit current is increasing. This is short circuit current, and so this is open circuit voltage. So we can see both are increasing. So what are we doing here? Are we increasing the irradiance or we are increasing the temperature? Which one of the two? And same in the both graphs. Here also same effect is has been shown. So this is the effect of, is this an effect of temperature or irradiance? We are going to see it next. Any guess? Or you know the answer as for the what we have discussed in the lectures? Okay, then let us see. We will see that. So this is a very simple question. So who would like to answer? So it is mentioned that fill factor of solar panel is 0.75 and open circuit voltage and short circuit current are given. Then we have to find the maximum power delivery by the solar panel. So first of all, what is fill factor? Can anyone answer? What is fill factor? Sorry. Anyone? So it is V max, I maximum, or voltage and current at the maximum power point divided by VOC IOC. This is given as 0.75. We want to calculate the maximum power delivery. So we know that maximum power delivery will be VMIM. So this is, so PM is 0.75 into VOC into IOC. And this comes out to be, anyone who has calculated this value? Quickly calculate this. What will be the value of the maximum power? This is very simple. It is 972 watts.
972.
Correct. So this is the next question. So we have this solar cell output current. Right? We have this model of solar cell where we have this light generated current. Then we have this diode. Then the shunt branch. Then this is the series branch. Here is voltage. This is I cell. We can call it V cell. This is RS cell, RSH cell, ID, and this is IL. So, which of these answer is correct? Which of these options is correct? You have to apply simple KVL, nodal balance equation. Here, ID is this I naught raised to power G V cell plus I cell R cell minus 1. This is ID.
Answer A, sir.
Answer A. Anyone else? How did you get reach to answer A.
Yes, yes.
So you see, this is IL. This IL is dividing into three parts. ID plus I shunt plus I cell, right? And we want I cell. I cell is IL minus ID minus ISH. So now once again try to correct your answer. Which one will be the answer now? You have all the values. You have IL ID is here. I have written, and ISH you can write that this voltage is V cell. So this voltage will be V cell plus this drop I cell RS divided by RSH. Now you have all the values. So you can put these values in this equation. So what will you get? Anyone? If we substitute all these values, we will get this answer D. Because I I cell is IL minus ID minus ISH. So this is ID, this is ISH, and this is IL. So D option is correct.
But in the slide it is showing answer A, sir.
Oh, it is showing D.
In, in the starting of the slide, you have shown, you have written that I cell is equal to IL plus N. In the first
Where?
slide, sir.
This. What's the, uh, where you are showing? Here.
Here, sir. Here, sir.
Oh, sorry.
Starting.
This should correct. This should be minus. I will correct
Okay.
this. This is
Okay.
minus.
Okay. Okay.
So you told the answer based upon this equation, right?
Yeah. Yes, sir.
No problem. So, but
Sorry.
now it is correct, right?
Yes. Yes, sir.
Oh, it is clear because
Okay.
it is
Now
simply
it is clear, sir.
KCL, right?
Yes, yes, I know.
Okay. So sorry for that. I
Uh-huh.
will correct it. So answer D is correct. Now we will see that the effect of temperature and irradiance on the profile, IV and PV characteristics. Can you answer this question before discussing? What is with the increase in solar irradiance level, cell VOC and IC will increase or decrease? Both will increase. What will happen? Or they remain constant? What will happen to the VOC and IOC? ISH? VOC increases and ISC decreases.
B, sir. B.
This is not correct. VOC decrease. B. You are saying B.
Yeah.
This is also not correct.
Solar radiation.
We will see. Okay, let us do it. Let us see how this will happen. So answer is that both will increase. One will increase linearly and one will increase logarithmically. Let us see how this will happen.
Okay.
So we have seen. So we have seen this equation, right? I cell is IL minus I naught minus ISH. We can further write it like this. I naught is for V is the voltage across the diode. Let me draw it here. This is V cell. RSH. So we want this voltage. This voltage. This is VD. So and this voltage will be this V cell plus this drop. Correct. So it will be V cell plus I cell into RS divided by eta VT minus 1 minus ISH. So current in this branch is this voltage across this resistor RSH divided by this resistance. So it is same as this V cell plus I upon RSH. Correct? Now what do we want? We want to see first what is the relationship I is for short circuit current and for open circuit voltage. Let us take the first the short circuit current. So what will happen if we short circuit these two terminals? So what will happen? This voltage will become 0. So this I cell will become IL minus I naught. Now this voltage is 0. So I cell RS upon eta VT minus 1 minus this voltage is 0. RS upon RSH. And this RSH is very big as compared to RS. This is in kilo ohms. So this we can neglect this also. This is 0. And this also we can say this is also very less. This is very small because RS is very small. So this is 0. So e raised to power 0 minus 1. So this entire quantity will become 0, right? So I cell will become IL, and which is same as short circuit current. So this short circuit current is approximately varying linearly with respect to this light generated current. So any doubt up to this point? Okay. So then let us move to the open circuit voltage. So this is clear, right? So increase in IS short circuit current is linear, which is clear from this. So if we see the open circuit voltage, what we have to do? We have to open these two terminals. So if it is these two terminals are open, then I cell will become 0. So now we have to substitute this again in this first equation. So what will happen? This I cell, which is 0, it becomes equal to IL minus I naught e raised to power current is 0. So E cell by eta VT minus 1, and this is V cell by RSH. RSH is very big in compared to VOC. This is in kilo ohms and this is some volts. Okay, it's around 20 volts you can say. So this is negligible. So we can neglect this as 0. I will write here. So now what is happening? This 0 IL minus I naught e raised to power V cell upon eta Vt minus 1. You can write it like this. Eta Vt. If you take log both the sides, and since IL by I naught is greater than 1, I naught is very small value. So this quantity is greater than, and if we neglect this 1 also, then you will get final expression as V cell, which is same as open circuit voltage as eta Vt ln IL by I naught. So voltage is increasing linearly. No, sorry, logarithmically. So any doubt in this? Is it clear? Am I audible? Hello? Am I audible? No response. Anil, are you there? Akanksha, can you hear me?
Yes, sir.
Okay, so is it clear? Effect of irradiance on PV characteristics, was it clear?
Yes, sir.
Okay, so let us move to the effect of temperature on PV characteristics. So what will happen that if we use these two equations, this one, this we derived in last slide, previous slide, and if we differentiate these two and we do substitution, we will reach up to this point. And here we can see that increase in voltage, open circuit voltage with respect to temperature is negative. But increase in current is very less, but the decrease in voltage is more. So overall, there will be decrease in power. So with increase in temperature, the output power will decrease. Open circuit voltage will decrease, but the ISC will short circuit current will only slightly increase. So I have one question for all of you. This we know that this maximum voltage is less than VOC, and maximum current is also less than short circuit current. Then why do we have maximum power at VMIM? Why not at these 2 points? Because here voltage is more, here current is more. Still we are not having maximum power at these points. What's the reason? To give you a hint, this is the PV characteristics. Right? For the bad trying, something like this. Uh, this is VOC. And somewhere here you will get IS. So why the maximum point is here, not here, or not here? Why A is the maximum point but not B and C? What is the reason? Because if we see what is power is product of voltage and current. Here what is happening? Voltage is zero. Here what is happening? Current is zero. The product is zero. We are having maximum somewhere in between. So this is not VOC. This is VOC. This is maximum. This is high maximum. So this is the correct answer. Let us move to the next question. So what is the function of gearbox in wind turbine power generation system? What's the answer? Anil, you were talking about the gearbox. C, during period of extremely high it is used to stop. No. Answer will be this B. C, first stopping, we use another control mechanism. So gearbox is used to increase the speed because rotor rotates at a lower RPM, but the generator need a higher RPM. So it will speed up, step up the speed as per the requirement of the generator. And what do we call this one? An enclosure that contains all other components of wind system. This is nacelle, right? And this one part is this transfer of torque from rotor to rest of drivetrain. So this is done by the shaft. So low speed shaft between the rotor hub and the gearbox. Then after gearbox we have this high speed shaft which goes to the generator. So next question is, according to BETS, the maximum efficiency of wind power generation is 79%, 69%, 49 or 59. What's the answer? I have already told this in previous slides somewhere.
59%.
Correct. This is 59%. Now next question is, wind power depends on which of these? Blade swept area, pitch angle, tip speed ratio, or all of the above? What are the factors that determine the output of wind energy system? Correct answer D is correct. So blade swept, all of these parameters affect the wind power. We can see here. So this is the output of wind curve and these are the points. So this we call it the cut-in speed. This is the rated speed and this is the cutout speed. Above this speed, there is no power. So we stop the wind turbine. Beyond the rated, we have to maintain the power to the rated power. Because beyond this V naught, speed is so high that the wind turbine cannot tolerate, so it has to stop. And below the V in also the wind speed is very less, so it is inadequate to for generation. So this is the characteristics which operates between these 2 points, and this is the power output. Here Cp is the coefficient which depends upon this lambda and the theta. Theta is the pitch angle. So this P naught will depend upon this rho, which is these environmental factors, which is rho, the air density, and the wind speed V. And the design factor is this AT. This is called design factor because once designed, it cannot be changed. So based upon our power requirement, this wind size, turbine size is decided, and which also decides the swept area and the size of the blades. We will see in the next slide. So, and then the control factors, this lambda, which is the tip speed ratio, and the pitch angle theta. So, answer is correct. Now, this question is in the fixed speed wind turbine. The speed of the turbine is controlled by controlling the following. So, what do we control to maintain fixed speed in the wind turbine in type 1? This is type 1 wind turbine because this is a fixed speed operation. Second type is the variable speed operation. So, what will be the answer for this? C, wind speed. No. No, the question is because how no. How can we change the wind speed? Because wind speed is not in our control, right? Wind speed is something that is the input to the turbine. We cannot change the wind speed. We have to change something else so that the output is a fixed speed. What is that element, that factor that we have to control? Correct. B is correct. So we have to change the pitch of the wind turbine so that from the wind speed that we are getting as an input to the rotor blades, we can get fixed speed at the output. So we have to adjust the pitch of the blades. So here we can see this is the a typical wind turbine, and we see this is the blade. This is one blade, this is second blade, and this arrow shows that if we move these blades like this or like this, then we can change the angle, pitch angle. So the orientation of blade to with respect to the wind direction will change, and based upon that we are able to maintain the fixed speed. So there are two things. One is this wind vane and this anemometer. These are our sensors which help us in ensuring this control mechanism. So this anemometer output goes to this control block of the pitch angle control block, and the wind vane will go to the another control block, which will control this motor. So these are our sensors for controlling these two motors. So there is a one more motor is inside this servo motor is there, which will control the pitch of the blade. So here you can see this. These are the different wind turbines from 1980 to 2018. The wind turbine rating is it's increasing. Now up to 2018, around 10 megawatt of output can be obtained from a single wind turbine. and the rotor diameter is huge, 190 meters. So one blade would be around half of this. It's 95 meters. It's a very big blade is required. So there are two types of wind system. One is onshore and one is offshore. So these big turbine we generally use in offshore because their wind speed are high. Wind speeds are higher, and we can get high power output. So these are the new wind turbines you can see. This is SG is Siemens Gamesa. So this is a company manufacturer. So it is manufacturing of 14 megawatt. This 14 stands for the power rating and this stands for this diameter of rotor. So this is the rotor diameter and this is the power output. 14 megawatt and 236 meter rotor diameter. This is for offshore, so inside the sea, away from the coast, where wind speeds are steady and higher. Onshore, 7 megawatt and 170 meter. There is another manufacturer which is Vestas, and it is manufacturing a 15 megawatt. So this is the highest. A single wind turbine can produce around 15 megawatt of output, and you can see the rotor diameter is very huge. 236 meter is very large. So we have such big wind turbines right now, and this will further increase in future. I think this is already done. So now, if you have any doubts, you can ask any questions. We are done with the questions for week 2 material. So now I would like to take some here from you. If you have any doubt in week 2 material, you can ask. Any doubts from week 2 material? So, Akanksha, you had one doubt on that last time you had asked on that synchronous generator operating at asynchronous speed. So is it clear or do you still have that doubt?
I mean, it's all depend upon the control action, right? All the controlling technique.
Actually, when the speed is changing, right? Because it is a synchronous generator, so it has to.
I have a doubt because it's going against the theory. Like we have studied
No,
synchronous generator always run on the synchronous speed. Then how can it will be run as a asynchronous speed? That was my doubt basically.
so it's still a doubt, right?
Yeah, kind of.
Yeah. So okay, I will clear that doubt. So what is happening that phenomena is still applicable here. So what do we have? We have synchronous speed is correct. This is correct, right?
125 p.
NS is 120 F by P. So here pole is fixed. We are not changing anything. So here now the two things are this speed and this frequency. Correct? So if I change this speed, then this frequency will also change. But this formula will still hold. Still this is synchronous speed, but the frequency will not be. Suppose the frequency is 50 hertz, then what will be NS in that case? What will be the NS in that case? Suppose it is a two pole machine. It will be 3000 RPM, correct? For a two pole machine. For four pole, it will be 1500 RPM. So this formula is still valid. So if we are changing the synchronous speed, then frequency will also change. Same thing is happening here. This is valid, but what is happening? The synchronous speed itself is changing, and as a result of that, frequency is also changing. Because as the wind speed is changing, the gearbox is fixed, almost fixed. It will change the speed which is the input of generator, and as a result of that, the frequency of generator changes. But because we want the frequency here, the generator is there, so here it is getting some v speed, wind speed v, a lower value. Output here we can say frequency, it is giving some frequency which is lower than, and here is the grid, but we want a frequency here which is a 50 hertz. But when the wind speed here is less, this frequency will not be 50 hertz, it will be something else, it will be less. So we have to do something in between so that this frequency can still be maintained at 50 hertz. So that work is done by this converter in between. Synchronous operation is still going on, but the difference is the synchronous speed is different, or different wind speed, and as a result the frequency is also different. So that is why we have to do something in order to maintain that 50 hertz, because we want to feed only, we want to feed voltage and current at 50 hertz only. But the generator is generating at some other frequency, we have to change it. So using converter we do it. With appropriate switching we can do that. We can change the frequency and so that the output is 50 hertz. It is a good doubt, you can say, good question. Any other doubt? If no, then we can do one small problem. One example. So, are you sure there is no doubt? And let me drink some water. So, is there any doubt in week 2 material? If there are no doubt in week 2 material, then we can do one small problem on wind system. If you have any doubt, you can ask me in between also. So there is one rectangular land, and on the 4 corners we have 4 wind turbines, WT1, T2, T3, all are of same specifications. So the specification is given as follows. So blade length is given. Blade length is 52 meters. Then we have rated wind speed. Rated wind speed is given as 12 meter per second, and cut-in speed is given 3 meter per second, and cutout speed is given 18 meter per second, and air density is also given. And following wind profile is given. Wind speed is there. This is wind speed, and this is time. So 8 to 11 a.m. to between 11 a.m. to 3 p.m. Then 3 p.m. to 6 p.m. 6 to 10 p.m. So this is the data. So, so can you tell me how to proceed for this question? So we have to find the renewable energy output for this farm for 1 day. So what will be the output? It will be megawatt hour. So any idea how to solve this question? So there are 4 wind turbines with same specification, and we have to find the net renewable energy output with this data given to us. And we have these speeds also. Based upon what we have discussed till now, uh, can you suggest a way to solve this question? Anyone? So let me first draw this curve. There is a power versus wind speed curve which we have seen in the previous slides. It is something like this. And after this, our output is 0. So this is the cutout speed. This is our rated speed, and this is our cut-in speed. So we have to first of all, and we have this formula for winds. So this is also given. Okay, so all these things are given. Now we have to find the wind out total output power or energy for the day. So what we have to do, what we can do is first we have to of these speed we have to check based upon this. So this curve only has been written in this equation. So we can see what is here when the speed is less than V in or it is greater than V out, the power output is zero. We can see here. Below this it is zero, beyond this is also zero. And between V in and VR, we have approximated it linearly. So we can write a straight line equation between these two points, where slope is this divided by this. And between this rated and cutout, the output is PW rated. So first of all, what we have to do, we have to find this. Here we know wind speed, we know as per this data, we know cut-in speed, we know rated speed. We don't know this rated power. So first of all, we have to find this rated power. Then we have to find the energy for each time block. Based upon this formula, we have to see what is the wind speed, and depending upon the wind speed, we have to choose whether it is zero, this or PW rated. So let us first of all see based upon wind speed what will be the PW among these three for each of the time block. So let us start with 8 to 11 a.m. So here the wind speed is 6.2 and the cut-in speed is 3. The wind speed is more than cut-in speed, but it is less than the rated speed. So power output will be as per this. So I'm writing here as PW2. I'm writing for this 2. So this we will say this is PW1. This we will call it as PW3, and we will call this one second expression as PW2. Let us write this as PW2. Now let us move to the next time block. So here we have 11 p.m. to 11 a.m. to 3 p.m. 5.6. Now we have to again check with this. So this speed is still 3. This is 12 and this is 18. So this 5.6 is still between in this range. So it will again be PW2 expression. 6.5 is also in the same range. Now we have to check for the 6 to 10 p.m. This is 14.3. But 14.3 we see this falls in this range. 12 to 18 between V rated and cutout. So this will be PW3. So power will be constant here between this wind speed range. From 10 p.m. to 3 a.m. it is 15.5. Speed is 15.5, which is still in this range. So we can write this expression as PW3. But now from 3 to 6 a.m. we see the wind speed is 18.4, which is above this cutout speed. So for this expression will be PW1, which is 0, which is 0 only. And from 6 to 8 it is again between this, which is the PW3 or the PW rated. So now the next step is to find the rated power, and we know that PW rated is half rho A V's cube. So we know rho is given 1.23. So for PW rated, we have to take the rated speed, and which is 12 meter per second. Area we have to find in this. So we know this, we have this value, we have to find the area. So area swept by the rotor blades that we have to find. So this area will be pi r square, and blade length is given. Blade length is 52 meters. So it will be pi into 52 meters square. So what will be this value? Can calculate. Did you calculate? What is this value? Anyone?
894.
8494.
8494 meters square.
Correct. So this is 8494 meters square. So if we substitute this in this equation, all these values, what are you getting? Rated power as?
Um,
So you have to
one,
do 1 by 2 into 1.23 into area of 8494 into rated speed is 12 cube. This you have to do. So this will come out to be how much are you getting? So you will get this 9.028 megawatt. Okay, you can check. So now what we have to do, we have these values. For 3 time block, we have this PW rated. And we also have to see the duration for this. So this is duration is 3 hours. From here, duration is how much? 4 hours. This is again 3, 4, 2, 5, 3, and 2. Okay. So now for each of these time block, we have to calculate the power. So final total power will be this PW for time block 1, for time block 2, 3, 4, 5, 6, 7. 6 is anyway 0. And if you want to calculate total energy, so you have to multiply each the duration. First is 3, second is how much? 4, 3, 3, 5, then 3, 2. So this is 0. This and these two we have to same as. So you can write PW rated into sum of these three. 5 plus 8, it will be 10, plus here these two values we have to calculate. Oh, I think I missed one. Something I missed one. PW5 I missed. So we can calculate this. Let us calculate it for one first time block. PW1 is PW rated into V minus V in divided by V rated minus V in, which is 9.028. Wind speed is 6.2 minus 3. Rated speed is 12. So how much? Can you calculate this, Anil? 9. So this will be your for first time block power output. Similarly, you can calculate this for second and third power output for time block. And then you substitute the values here, you will get the final output. When I will upload the
PW1 is 3.2, sir.
3.2, okay,
3.2 megawatts.
3.2 megawatt, thank you. So similarly, you have to calculate. So you will get PW2 as PW2. You will get this as 2.608 megawatt, and PW3 will be 3.5109 megawatt, and then we have to substitute this. So final output, final answer you will I have not calculated. Just you have to just add it. So when I will add this, just upload these slides. So I will also upload the solution for this and final answer. You can match your answer. So if you have any doubt, you can ask. Anything from week 1, week 2, or today's session. And if you have any suggestion, how should we improve these live sessions, you can also give your suggestions.
Sir, can you suggest me a textbook for this course, sir?
For entire course, there is not a single book, but for this today's for wind part, do you want to know for this?
Yes.
For
Yes.
wind one, I can suggest you can have, there is one Gilbert M. Masters, chapter 7 of Gilbert M. Masters, that you can refer for wind portion. So I have also taken some pictures from that book only. So you can refer that. The thing in detail is given in that book. So you wanted my email ID.
What is the title of the textbook?
Title, I have to check. Just
Give me your email ID also, sir, because when we have some doubts regarding any problems,
I would like to contact you.
Just a minute. Okay. Just drop me a message. I will send you the link for the book, or the name of the book. I'm not remembering the name right now. Okay, Anil, are you there?
Thank you, sir.
Okay, thank you. So time is up. Let us thank you for joining today's session. We'll meet same time next week, Tuesday from 6 to 8 p.m. and we will discuss the week 3 material.
Okay.
Also,
Thank you, sir. Thank you so much.
thank you. Please submit the assignment.